welcome you to today's session in Trillium Flow Technologies technical webinar series. My name is Andrea Bellinzeri, and I'm the Global Product Director for Isolation and Control Valves at Trillium Flow Technologies. Today, we'll also be joined by my colleague, Sanket Valimbe, who is the Technical Development Manager for Trillium Flow Technologies UK. Our presentation will focus on a digital solution for control valve. So throughout this presentation, you will be able to ask questions at the end of the presentation. To do so, please use the Q&A box. We will answer at the end. Just a little introduction about us. My name is Andrea. I'm from Italy. I have 22 years of experience in the valve industry, in both product management and international sales position, across a range of different industries, including power, nuclear, oil and gas, petrochemicals. I'm holding a bachelor's degree in mechanical engineering from Parma University. Together with me, I have Sanket Valimbe, who is Technical Development Manager. As said, Sanket has over 15 years of engineering experience and is currently working as our Technical Development Manager in Elland, England. Sanket holds a master's degree in mechanical engineering from the University of Sheffield, UK, of course. Few words about Trillium Flow Technology. Let's have a quick overview of our brand portfolio. So our name, our product name are synonymous within the pump and valve industries. With pump brands, some example, we have Flowway, we have Gabioneta and Thermomechanica, Rotojet, Wemco, and WSP. As valve, we have Atwood and Morrill, Isolation and Check. We have Hopkinson, again, isolation and glow valves. Blackborough, control and choke valve. Batley butterfly valves. Hiller actuators. Red Point as fast track solution. Saracen and Sebeam in France as safety valve. And last but not least, tricentric triple offset valves. On the top right picture, we can visualize the Trillium global presence. We have about 21 facilities from west to east, so we are covering the entire globe. Those are not only manufacturing centers, there are also service centers. Some interesting milestones on our history. We have a long heritage of innovation spanning 190 years. So you see, we start in 1828. We're continually adding new products and service to our portfolio. The last two editions were in 2020 Red Point and 21 the Thermomechanica Pompe from Italy. A good idea for today is also the virtual trade show. If you are interested in having a look at our products, we welcome you to register at virtual.trilliumflow.com and enjoy the show. You can learn about our service offering and see what industries we are able to serve. Today, we're going to talk about these four important points, which we call market trends. So you will hear about the process efficiency and the cost reduction in supply chain. The point is how Trillium will be enabled to share cost saving to the client. We have as well the reducing environmental impact energy efficiency. That means that by connecting our asset to the plant's control and data acquisition system, our clients can manage their entire process and gain efficiencies. So remember, information from Trillium will support an improvement in the environmental governance while reducing the associated compliance cost. That's our message. Regarding the remote control and automation, this is called Trillium Customer Digital Experience Innovation Area. So Trillium can provide 24 hours a day monitoring and monthly reporting to increase the on-site service capabilities. Decision-making driven by big data. The Trillium's cloud-based enterprise will enable our clients to have data readily available. Before Internet of Things and wireless monitoring and 4.0 industrialization, which will be explained better by Sanket shortly, generally a product was used to be operated until failure. So if the asset fail, both the plane maintenance engineers and let's see all the technical guys would be deployed into action to identify or solve the issue. This, of course, you can imagine, would lead to high cost, long downtime, missing production. This is a huge impact. We try to avoid this. We want to propose a solution to predict this happen and prevent this happen in advance. Customer pain point, what do we want to address here? What are the major pain points? One of them is certainly the underperforming valve due to erosion. What caused this result, this erosion? We are dealing with fluids, which are mainly hydrocarbons, with traces of sand. And throttling these fluids, the local velocity increases. And this, as you can imagine, can lead quickly to a rapid erosion of the valve trim. It's just a matter of time. It will happen. So most conventional control and choke valves are designed with labyrinth-style trims to achieve multi-stage pressure letdown. This will cause also sand blockages. Now, I'd like to pass the ball to Sanket, who will drive us to the core of our speech.
So, hello everyone. So we have just seen how the valve been used before IoT or call it IIoT, and the result of it is expensive catastrophic damage. But what is IIoT? I mean, what exactly it is and how it could be beneficial to its end user. So basically, it's an abbreviation of Industrial Internet of Things, which is a vital element of Industrial Revolution 4.0, which just Andrea mentioned, which is the current era of connectivity, advanced analytics, and automation. So basically, the industrial machines have been producing the valuable data for many years, which can be collected in a real-time environment and then processed through analytic software to track efficiencies, life cycle, and potential chances of failure of each of the machine. So this technology can be used in process industry, as we are trying to do that, as it can offer efficient maintenance process, eliminate manual intervention, better safety to personnel working around the asset, and mainly it can help to reduce the production cost, which is we are targeting we are addressing in this solution. So with this technology, the sensors fitted around control valve can continuously monitor its physical properties, and the monitor data can be compared with pre-established baseline. So if the valve starts operating below the pre-threshold value, the system sends an alert to the plant supervisors and engineers. Thus, malfunction valve can be addressed well in advance, preventing costly delays and production losses. So this is basically an overview on how we are looking at using this technology in our products. So how we utilize IoT to address customer needs using our product expertise. So our fundamental commitment is to develop a sustainable solution so that sustainable solution. So it basically took us years of strategy, planning, and thousands of hours to develop a solution that could address dynamic and unique customer needs. So harnessing the power of cloud architecture along with data analytics tool, our system utilizes the innovative smart technology to monitor performance degradation of a mission critical valve. So as you see in this slide, we equally considered every corner, the technology, the data analytics, our product expertise, and last but not the least is a customer need. So this is I'm going to talk you through, like, what exactly the solution is. I'm just going to give you a bit of an overview. So Trillium's new technology digitally transforms existing system to give total care. It provides real-time condition monitoring, enabling plant preventive maintenance, minimizing downtime and improving productivity of the plant, thereby increase machine time, machine uptime, and operational efficiency. So these are the clear benefits to customer using our technology. We aim to use a big data. I mean, all these machines, all these equipments, all the valves and the things basically generates a lot of data, operational data. So we aim to use big data as a service. Our digital platform can handle large data sets 24/7 to better understand operation of a particular asset. The customer will have full access to their asset operational data. I mean, of course, they own the data, and they can deploy advanced analytics through our software to obtain accurate information about condition of the assets. So we have also given a touch of predictive analysis in our solution. So the data generated from a digital platform can be used to predict machine condition and anticipate any failure, so that the operational efficiency can be maintained. So basically, if we can anticipate the failure of any particular valve, you can deploy the forces accordingly. And when it comes to performance optimization, we emphasize on services we provide to the customer. So by leveraging Trillium's remote monitoring capabilities, the extra cost of on-site valve service expertise can be eliminated. In fact, the system can be set up to maintain direct contact with the Trillium Services division, providing rapid response instructions for detected failure. So basically, we can also we also work along with the customer to analyze the data or to analyze the predicted failure and act accordingly. Lastly, our solution not only focus on a bespoke requirement, but also it can be expanded to suit a turnkey solution. So our scalable gateway infrastructure allow for a remote real-time monitoring of hundreds of assets worldwide from a single location. The system can function as a standalone, or it can integrate into the existing infrastructure. So basically, I mean, this will allow end user to monitor multiple assets from their DCS control system wherever it is located. So we have seen the overview of the solution. So let's see how let's take a look like how it's gonna benefit the customer. So take an example. I've taken an example of a 4-inch duplex control valve in a severe service application. So as you can see, I've taken an example of oil and gas production system. But the severe service application can be found in all any kind of a power station, refineries, or any industrial plant where basically large mass flow rate at a high differential pressures are needed. So in this particular example, the valve can be handling production and injection fluid, which are highly corrosive and erosive in nature. So basically, if you see on the left-hand side of the slide, you can list down the fluids. So the fluid could be a mixture of these, or it could be a standalone, but the fluid will eventually erode away the valve in a matter of weeks or in a matter of months, depending on the service condition. So we assume the valve is operated to failure, which means it's without having Trillium's condition monitoring system installed on it. And upon failure of the valve, you basically have to deploy the emergency inspections, and it would cost nearly $300. So I wanted to highlight this is absolute minimum. If the valve is located offshore on FPSO, middle in the North Sea, then this cost would be definitely in thousands. So it all depends on where the valve is located. And then there would be an emergency labor cost, which is again $600,000. This will go in thousands where the valve is located. Then you will need a soft spare in an emergency spares that would cost nearly $2,000. And along with that, you will need a new trim set, which basically, the plug, the stem assembly, cage, disc stack seats that would cost like around $6,000 with a 12 weeks lead time. So this is the critical point, because at this point the supply chain could be long. If any of this component is made of exotic material, it's going to take a really long to get that part back onto the valve. So, and it's going to cost a lot as well. So this is the minimum cost that I'm showing you here. The additional software you would need as well for a future maintenance, that would cost you nearly $2,000. And you would need to expedite everything to get it quicker, because you can't wait for a 12 weeks, 14 weeks, and that sort of time frame. It would cost you $3,000. Again, it depends on how the supply chain is a setup for that particular component. And finally, when you have all these components, you need to fit them back into the valve. It's again cost $600. So it's again, depend on where the valve is located. So everything put together, the cost, the emergency cost, the inspection cost, the power cost would be nearly $14,500. It looks very small amount when you think about oil and gas production system. But the major cost attached to it is the production downtime cost, which could be hundreds of thousands of dollars per day. So if this valve would have been equipped with the Trillium Smart Valve technology, then we reckon the potential saving on the emergency cost would be 45%. And downtime cost could go down between $50K to $100,000 a day. So this is the cost we're targeting, that how we could minimize this downtime cost with using our technology. So we talked about the market trends. We talked about customers' pain point. We had an overview of our solution. We also touched base on the example, like, the potential saving that this solution can bring to the customer if this system is in place. Now let's take a brief look at the architecture of the dashboard. Is basically the software, and let's take a look and feel of the software, and where you can see all the critical information on the one screen. So when the system is up and running on any of the asset, the first thing you probably have to do is to select the asset, where the asset is. So you have this drop-down boxes here, as you can see. You can select the site, you can select the asset tag number, and you can click on the hit button and it will populate the necessary data. You have also option to use the interactive map. So you basically zoom in and zoom out on the map, and to select the asset, if you know the exact location of it. You have a table under there as well, which can give you an overview of the assets, the tag numbers. So you have an option to select that way as well. So when you submit this information about the asset, the dashboard will appear, which displays the flow parameters. As you can see here, the upstream and downstream pressures, the valve position from the digital positioner. You will have a flow meter reading. Basically, it's the flow rate going through the valve. You have a fluid temperature. The fluid type, it depends on SG, the specific gravity of the fluid, and you have a health of a battery and a signal strength of the connected equipment, which is it's quite important parameter to keep an eye on. So all these readings are taken live, and the refresh rate can be selected according to the criticality of the asset. So you basically set the refresh rate that you need in a few seconds, you need in 5 minutes, that basically consume the battery needed for each and every the instrument. So you can select that refresh rate according to the need of the process. So the most important page here is the configuration, where the threshold can be set. So as you can see on this page, you have a refresh rate to select. As I mentioned earlier, you can select the fluid type, which is going through the valve. You can select the flow characteristic of the valve. It's equal percentage, linear, whatever is the trim installed in the valve, you can select here. You have a CV values that you can put in there and save CV max for that particular valve. And on the right hand side, as you can see, you have a threshold value. So you can set a CV amber, CV red. Whenever you want the alarm to pop up, you have a pressures, temperatures, flow rates, all this information you can set as a threshold for the system to look for. So this configuration page is not just limited to this parameter you see on the screen. The other parameter can also be added according to the customer needs. So, we work with the customer what exactly they wanted to set as a threshold, and we can tweak the system accordingly. So we have seen the dashboard now. We have seen the different features, the different buttons, and how you can select the assets and everything. Now let's take a look at data storage, connectivity, and asset. The access. So the first and probably the most important instrument I probably would say is a digital positioner or a smart positioner. So our platform is flexible to accommodate input from industry-leading positioners. So our system can take inputs from various interfaces such as HART, smart positioner, field bus, etc. So any interface you have on site, our system can be tweaked to take those inputs. So basically the system is flexible, and customer don't need to consider changing their existing positioner or any other instrument. When it comes to installing additional sensors, data loggers, transmitters, gateway system, we partner with the industry-leading supplier and get those instruments suitable to hazardous zone, pressures or temperatures. You have a different temperature limit for the particular fluid, so we can bring those suitable instrument, into the package, and that can be supplied. So that's flexibility there as well. The important thing is the remote connectivity. So during our development stage, we focused on this attribute, so we developed the system that can be connected using variety of networks such as Ethernet, GSM, Wi-Fi, long-range radio, or even the satellite. So we basically, if the asset is in the confined space or somewhere remote, where the selection of network is limited, we can work with the available network and get the instruments connected and get the data into the software and analyze. So that flexibility is there as well. The most critical part, or probably the next critical part, I would say, is the data storage. We understand, the data is very, very precious. It's very classified with some customers. It cannot be shared with the third parties. So we have given an option to save this data. So you can, customer can deploy a cloud-based server, or, they can have a Trillium servers, either it's on cloud or either it's on a premises. Or customer can use their own server. It's definitely flexibility is given there, as we understand data is very critical. So in any of the cases, we ensure that the data and the network is secured and protected at all the time, because that is something everyone is looking for in any kind of this digital scenario, like how the data is protected and secured. Then the alerts is probably the key, without which the system is incomplete. If you don't get the alert about your thresholds, then it's basically you're not getting the information of your asset. So once the data is analyzed by our algorithm, the customer can get alerts via emails, on dashboard, or text messages on the designated device. So that the necessary action can be taken in timely manner. So as I shown you previously, you can select your thresholds, and then you will get the alarm when the thresholds, when the process crosses threshold, and you can get the alarms on your selected device. So in today's, in all this digital world, we use the software. There is a very high software based, the product is this one. So the system is updated. We make sure the system is updated all the time, and it's a bug free. So we provide basically a regular software updates, which can be installed in few clicks. So there is no hassle, the software is updated, it's running slow. We make sure that the software is updated all the time. And again, I wouldn't emphasize more, as I mentioned previously, the security of the data is paramount. So all the dashboard and analytics software is enabled with a secure access PIN, so which is basically generated every time when the customer log in. So no unauthorized access to the data or unauthorized access to basically the software is permitted here. The system can be set accordingly according to the need of the customer here. And lastly, like, is probably another critical point is our system, with our system, customer can download the reports of condition of all the install base potentially to assist the operational planning and plant shutdown. So you basically, if you have a 10 valves, 5 valves, or 100 valves, you can basically download the report and basically, plan the operational or maintenance accordingly, according to the need of the individual valve. So we have seen the dashboard, the storage, connectivity, basically mostly related to the cloud and the software. Now let me take a step back and to give you to basically give you an overview of the approach we took to develop the this condition monitoring algorithm. So Andrea has talked about one of the issue in a severe service valve, which is erosion. And we understand that this issue is inevitable. It can be minimized, it can be detected early, but it cannot be avoided at all. So we basically address this issue, and we have came up with the approach to develop the algorithm around this issue. So let's take a quick look at the approach. So we started with the extensive lab test. So to identify the wear rate of different material, we supply this trim basically in different materials, and all these different materials have a different rate of erosion. They erode away. Some materials are softer, they erode away quickly. Some are harder, so they take a longer time. And again, it depends on the service condition as well. It's not just the material. So we need to understand how exactly this material erodes in a different conditions. So we basically developed a small erosion test bench to understand how these different materials can react to different erosion conditions. So as you probably know, the erosion rate is a function of concentration of contaminants, size of contaminants, specific gravity of the fluid, velocity of the fluid. So we basically came up with a number of permutation and combination of these factors to develop the erosion rate. And once we know the erosion rate of that particular material, we deploy that erosion rate using the computational fluid dynamics to individual trim. And this basically helps us to come up with a baseline for the algorithm. So, this is kind of a theoretical exercise that we did. So as you can see here, this is a little bit of a picture of the test bench. So you have a material samples like this, and the different condition been developed in this in this small container, and we analyze how this material sample erodes away. So to verify outcome of this CFD or this theoretical data, we developed a full flow loop that basically is a flow loop for conducting the erosion test on actual valve. So we created an erosion media with a different size of concentration, size of a contaminants, and different concentration of contaminants. We run it through the loop at a different velocities, which basically generated the erosion trend of that particular trim. And final results we compared with the CFD to basically understand the results we get from the empirical test are how close they are with the CFD. So that is the important part of the exercise we did. So on this picture, you can see a little flow loop there, where we have created the slurry mixture, or basically a mixture which is erode the valve. There is a little valve here. You can see there is a pump, and it basically pumps the flow through the valve. As you can see, this is a wired sensor we use. It's a small flow loop, so we didn't bother about going for wireless, but we can definitely offer wireless sensors here. And this is basically the flow loop. So we basically conducted multiple flow tests on the trim, evaluate the erosion trends from each of the trim, and as I said, I compared with the CFD results, and we further refine our algorithm, and that basically can be used going forward in any of the field like scenarios. So let's see a little further on the CFD studies. We did understand the effect of erosion at a micro level. So Take a look at the top left image. It shows erosion contours resulting from the study. The regions of the high erosion of the outer cage wall can be seen on the left and right hand side. These are the areas where flow velocities were quite high. So as you can see here, little high spots in these circles. So at that spot, the velocity was quite high. Take a look at the mid image. This is the one which shows the pressure contours of the flow. So the flow enters the valve, which builds up the pressure around the trim before it passes through the holes of the trim. And as the flow passes through the trim holes, the pressure drops, and then it recovers near the bottom. So as you can see, the flow passes through the holes, the trim holes here. And then there is a little of a pressure builds up and, around this area, and then it basically eases out towards the outlet of the flow. Now on the right hand side image, on this image, it's basically telling us the velocity contours. So as the flow passes through the trim holes, the velocity increases significantly due to the decrease in flow area. So you can see here a red spot. These are basically the velocity contours. So what's happening basically, the jets are formed as the flow exit the holes, and these jets are collide in the center of the trim. As you see, there is a little pressure built up here. So that's where basically the pressure is generated once the flow exits from the trim. Now take a look at the bottom images, which basically shows the velocity variation in and around the trim holes at a different rows. So we consider this trim, and then you have a multiple holes at a multiple rows, and these holes are of a different diameters to basically adjust the CV of the valve. And obviously, since the flow paths are of a different area, there is a different area for each of the row. And as you know, the velocity is different at a different hole, and there is a different erosion rate for a different hole of the trim. So, and another interesting thing to see here, when the flow enters, when the flow hits the trim, it hits in an angle. So basically, the difference in the velocities, and because of the velocities are generated at the hole patterns are non-uniform, and hence the erosion rate is non-uniform. So let's take a look at the how we use this understanding from this micro level study to understand the bigger problem. So we came up with a global erosion rate. So we basically understand the erosion rate of at a local areas, and from the local areas we basically come up with a global erosion rate. And what we did is we extrapolate that result to understand the valve, to understand the effect of change of the CV on the valve position, according to the valve position, and on the specific time frame as well. So if you see on this graph, you have two CV graphs. So you have equal percentage, which is the original graph of the trim, and you have one which is the eroded trim. So that's basically is something coming out of when you apply the global erosion rate to the particular trim, it shows the change in the CV according to the position. And then there is the average global erosion rate we apply to the trim to identify a CV change over the number of years. So as you see, there is a number of years. So we consider, like in this example, like 5 to 6, 7 years, 10 years timeline, but there is no trim that can last around this long time. So this is just an example I wanted to show for this presentation. But as you can see here on this image, the area of the flow path has changed over the time, and that basically reflects on the CV. So that's basically, the performance degradation at a micro level, at the macro level, sorry. Then we conducted empirical tests to validate this theory. We conducted multiple accelerated erosion tests. We started with a soft material trim, which we redesigned to suit the process condition of the loop. So we consider a bronze. We just wanted to prove the theory, so we considered the software trim here. The design CV of the trim was nearly 12.67, and the predicted change after the test was 18.97. So this is basically coming from the theory, 18.97, and then we set the similar conditions on the flow loop, and then we found the actual change in the CV was 18.15. Which is pretty close to what we predicted, which is within plus and minus 5% of the theoretical results, so which is what we expected. So it's pretty accurate. So if you notice on this graph, the solid line, the light blue line shows the theoretical CV, and is basically is the gray line shows the actual CV found after the test. So is pretty close. So, I mean, that's all the information, that's all the results that we have seen during our development stage and during our the testing. But how exactly customer will see all these results, how these results are represented or represented to the customer is the critical part of it. So we have an analytics dashboard on our system. So as you can see here, platform is designed with the interactive analytic dashboard to provide an overview of the equipment performance, along with the flexibility to deep dive into the area of concern. So you have asset information and flow parameters at the top. As you can see here, you have asset information on the left-hand side, your tag numbers, your asset name, your Trillium order number, valve ID, everything is there. On the right-hand side, you have pressures, differential pressures, valve position, flow rates, and then you have a set of data sets that you can select from the range. So you have a start date to select, end date. You can select your time frame, and then you have average time window as well. So you basically select if you need to average out your readings at a particular time frame, so that you can select. And once you submit this result, the graph will get automatically adjusted to that. And then on this side, you have a different legends. As I said, it's basically the flow parameters, the pressures, upstream and downstream pressures, the differential pressures, the flow rates. You can turn on and off these legends according to your needs. And then the automatic graph will update. But during all this operation, the graph is continuously updated as the data is keep flowing from the instruments. So you can keep getting the live reading as you play around with this analytic dashboard. The next page is you will see a little bit more details. You can visualize specific information such as CV change against the valve position. As you can see here, you can see the wear rate of that particular trim. So as you can see in the particular example, we have set a one position for longer time, and the CV has changed over the time. As you can see, the trend is a little bit upwards. You can see the CV has plateaued at this one area, and you can see there is the wear rate which shows the less noise in the graph. So you can see the wear rate according to the CV change. On the right hand side, you have a CV variation in a percentage. So basically, whatever the threshold that you have selected initially, you can see that how much the percentage deviation from the threshold. And then you have wear acceleration. So how quickly the trim is getting eroded, that basically can be seen here. So again, I can emphasize here on this plateau. One example, you can see there is a less acceleration compared to the rest of the test. And lastly, you have an alarm window, which provides information about the different threshold that you have set. So you have a P1, P2 alarm. You have your CV alarms, you have flow rate. You can select the temperature as well if you want. So all this can be set, and all this can be notified on the dashboard. And all you can see all this information on the one screen. You can set on the multiple screen. So it's basically as long as you can have your decision informed in the right and timely manner. We can set up all these things according to the need. So all this is a bit of from the technical point, from the perspective of how we deploy the clouds and the servers, the sensors, the theoretical part of the erosion. And now I will hand over to Andrea to summarize this session. Over to you, Andrea.
Thank you, Sanket. Thank you very much for your detailed explanation. Seen we have a lot of questions in the box, even if, to be honest, most of them have been covered during the presentation, but we will answer soon. So let me recap a little bit what we discussed today, what we have presented today. Conditioning, monitor, and diagnostic will, of course, provide information and data service, which will lead to predictive analysis due to our algorithms and anticipate failures. This is a performance optimization of valve, line, system, plant, due to the mitigation of risk and money savings. So we're proud to say this is our turnkey solution and leverage capabilities to move up the value chain. In a nutshell, real-time valve performance monitoring, erosion mapping of trim parts, real-time monitoring single or hundreds of assets in multiple locations, all of them 24 hours a day and 360 days a year with one software for all valves. So this is how we help on improving sustainability. And thanks everyone for listening to us today. Let's go through the Q&A session now.
Yeah.
Second.
All right. So I can see a lot of questions there.
There are some interesting questions. Some of them have been covered already during the presentation. Yeah.
So I'll go the first one. Will your monitoring system work in a high temperature molten salt application of 600 degrees C? So what I would say is a quick answer to that is yes. We can select all our instrumentation to suit the temperature. We can what exactly customer wanted to see in that application is something we will analyze and tweak that system accordingly. And I can understand in a molten salt application, you probably might want to say if there is a blockage and things like that, because the crystallization of a salt. And if the temperature maintains throughout the system, that probably could be the critical. But I'm just guessing. But yeah, we can work around with the customer requirement in that sort of area, and yeah, we can provide a system suitable to that. Can you monitor upstream and downstream pressures, liquid flows, gas flow, temperature? So yes, I think I have already covered that in the presentation. We can monitor every single parameter that has been asked here. So yes, that can be done. Can the data collect data from the valve, digital positioner, heart? Yes, yeah, we can tweak our system to fetch data from these positioners. That can be done as well. So what kind of the sensor we use for monitoring? Is this based on sonic reading or temperature, pressures, vibrations? Right, yes. The sensors will be delivered with the valve. We will deliver with the package. Well, again, it depends. Like, we can supply the sensors along with the system, or we can use the existing system or existing instrument available on the site. So we can work with the customer on that front, how they want it to be done. The temperature and pressure and vibration, all these, the temperature and pressure sensors, all these we can work with our partners, and we can select the sensors according to the system on place. Do you have example of how a dashboard look like? Yes, I think I've shown that. That has been covered. How accurate is the diagnostic system? Yes, we have covered that as well. What we have seen is plus and minus 5%. So we aim for that accuracy. Can you monitor leakage of the valve? So yes, it depends, like, where exactly this is happening. So as long as it affects the It affects the performance of the valve. Definitely that can be sensed. Like, if you see there is a leakage, there is a difference in the pressures, and that can be notified, and you can definitely those kind of information you can see on the dashboard. We can set the dashboard accordingly, so that can be done as well. Yes, I think that I've covered most of them.
Yeah. Seeing, for example, if we have a Trillium positioner, no, we don't have a Trillium positioner. We use all the positioners that are available in the market according to customer specs.
Yeah, but yeah, okay. The system is flexible to take inputs from the positioner that you have already. So it's the most important thing.
Okay.
Yeah, that's it from me, I guess.
I think that's it. If we miss something, reach out. If you want to have more details, please reach out to us by email at info@trilliumflow.com, and we'll provide the answer directly. Thanks again for listening to us today. Wish all of you a great day.
Thank you, everyone.
Thank you.